Good morning, everybody. So in the interest of time and not to steal too much time from the speaker, I will start the session. So my name is Elena Valker, and I'm the current president of the UCA. And we are here today to recognize the European Control Award. The European Control Award was established in 2014 by UCA, and it's meant to recognize outstanding contribution by a young researcher in the area of systems and control. The recipient, one is of the eligibility condition, apart from excellence, of course, is that the recipient must have spent a major part of his or her career in Europe, and at the time of nomination must be working in a research institution or company in Europe. So the award comes with the invitation to deliver a plenary at the European Control Conference, which is what happened today. And the award recipient of the 2025 European Control Award is Timm Faulwasser for contributions to optimization-based control of nonlinear and stochastic systems. So let me briefly introduce the speaker. So Timm is a professor in the School of Electrical Engineering, Computer Science and Mathematics at Hamburg University of Technology. He studied engineering and cybernetics with a minor in philosophy. That impressed me, actually, at the University of Stuttgart, and obtained his PhD from the Otto von Guericke University in Magdeburg, Germany in 2012. So he was a postdoc at EPFL and a senior researcher at Karlsruhe University of Technology. So he has also amazing experience as a volunteer. He was a member of the IEEE CSS Conference editorial board and associate editor of the European Journal of Control. Currently, he serves as associate editor for IEEE Transaction Automatic Control, Mathematics Control System and Signals, and last but far from being least, the IEEE Control System Letters. So Timm received the 2021-2023 Automatica Paper Prize. And the talk today is entitled Dissipativity, Optimal Control and Turnpikes, How to Get from Willems to Wasserstein and Deep Learning. Thank you very much.
Indeed, I want to take you on a journey which reflects a bit the years spent after my PhD in terms of research. And I'll start with something very bold. We are in the year 2025. The first quarter of the 21st century is already past. So let me give you my take, what are two among the many landmark developments in systems and control from the previous century. And given the title of my talk, it's not too surprising that in the left corner, I picked the optimal control twin breakthroughs, that is dynamic programming and the minimum principle. And what always strikes me with surprise that Bellman published about dynamic programming in 1952. In 1956, Pontryagin and co-workers did put forward the minimum principle, but at the same time, the minimum principle was kind of rediscovered because Hestenes and Isaacs, working on calculus of variations and on differential games, had already came across it, but didn't realize its value. They put it in some memorandum because all three of them, Isaacs, Hestenes, and Bellman, were working at the Rand Corporation down in California at the time. The other contender is dissipativity for open control systems, as put forward by Jan Willems in these two 1972 landmark papers. It's back there. Thank you, Dominique, for showing me. And the amount of research that dissipativity as a concept for systems and control has triggered is so broad, I cannot touch upon all of it. It's sheerly impossible. I will focus on the links and commonalities between dissipativity and optimal control, and I will try to convince you that there are more links and commonalities that we commonly are aware of. So the trajectory for this talk starts with dissipativity and optimal control. I will then explore what is called the turnpike phenomenon together with you in different variations. I will explore it in port Hamiltonian systems and stochastic systems, but of course we will start easy in a deterministic setting. And then I will flip and mirror these insights to understanding model predictive control, and I will try to share some recent insights of our research, how we can transfer these ideas to come up with training formulations for deep learning. So in essence, there are two main lines of thought in this talk. That is analysis, more to be precise, dissipativity-based analysis. And the other line of thought is dissipativity-informed design of control schemes or of formulations for learning. Now, what's the starting point? The starting point in Willems' own words for his work on dissipativity was the idea to generalize Lyapunov inequalities to systems with inputs and outputs. And we all know Lyapunov inequalities. We have the decay or we have the change of the Lyapunov function along trajectories, which should be upper bounded by a non-positive decay term, which exactly vanishes in the equilibrium whose stability we want to study. And the ingenuity of this idea is clearly that I don't have to compute trajectories anymore. I can evaluate this condition at each point in the state space. It often turns out to be easier than computing trajectories. What Willems did is, he went from the closed system to system with inputs and outputs, and of course, then naturally the U has to appear on the left-hand side in the F, in F of X in U. If he would have stopped there, he would have precluded what Sonntag did in 1983 in terms of control Lyapunov functions, but this is not where he stopped. He added a supply rate which models the interaction of the system with its environment. And of course, talking about supply, there is a second, I would say, ancestor or precursor to dissipativity, which clearly is passivity, which at the time in the 60s was more like an operator theoretic concept. You were looking at how does a system translate inputs into outputs. It has its origin clearly network theory, electrical circuits. Okay, so let me give you not a really formal statement, but a tad more formal statement. We take this state space description with inputs and outputs, and we look at the set of all trajectories in terms of x, u, and y, so boldface letters are my trajectories, of a given length, which satisfy the system. And we call this set, in Willems fashion, you could say that's the behavior of length t. And then we can have an ad hoc or rough definition of dissipativity saying the system is dissipative with respect to a supply rate if there exists a non-negative storage function such that for any time horizon I pick and any corresponding element of the behavior, the dissipation inequality holds along this element of the behavior. And of course, you can always take 2 points of view when you look at dissipation inequalities. When you start from Lyapunov, it's tempting to always look here at this pointwise condition where of course, to compute the full differential on the left-hand side, they need certain differentiability properties. It turns out that for optimal control, this integral view on a dissipation inequality is actually something which is super, super helpful. And I show you several instances where this comes to our aid and helps us. Now, let me first ask a simple question. Some of you might know this. How can you characterize dissipativity? And if you look in the 1972 paper, I think on page 10 or something, so very early on, Willems gives what is called the available storage, and he uses this to answer the question, how much storage / energy can I extract from a dissipative system? And the idea is you look at an open free n-time optimal control problem, which is constructed to maximize the negative supply, so the amount of energy you extract from the system. And you do this over all trajectories of the system. And then he comes about with this very elegant proof to show if and only if the value function, which we call here the available storage, is bounded on the entire state space, then my system is dissipative. And what strikes me with surprise, what struck me with a lot of surprise when I read this the first time, is that already in the very characterization of dissipativity, optimal control appears. And there is the sibling of the available storage. It's called required supply, which is a bit more complicated, but yet another value function of an optimal control problem, which gives you another if and only if characterization of dissipativity. So I think it's safe to say dissipativity from the early start builds upon optimal control concept. It's constructed around value functions. But if you look at the story, then there was one paper which precluded these 1972 two-parts papers of Willems and dissipativity, and that appeared a few days in the transactions of automatic control before he submitted his other paper. And what was he looking at there? He looked at infinite horizon least squares optimal control, problems of this form. Now you may wonder, 1972, the LQR was known at this time. The Apollo space missions, which relied on the LQR to a large extent, and Kalman filtering and other stuff, had already happened. Why did he look at this? Well, what he did change is he did not require any definiteness on this quadratic form which forms the stage cost. And the central idea in this paper is you use a dissipation inequality, and the supply rate you look at is the stage cost of your optimal control problem. If I would attempt to give you a walkthrough for all that happens in that paper, we would be here until lunch break because there happens so much in that paper. So let me just give you the two main things which always I find most impressive. He gives Willems gives us an LMI characterization of dissipativity about 20 years before LMIs became really computable. So he was way ahead of his time, and also characterizes the algebraic Riccati equation and a lot of other stuff. So you might safely say, hey, if so much happened in this first paper, what has he left to be done? Very fair question. The first thing which does not happen is constructive insights on nonlinear systems. This is what Hill and Moylan did, commencing in the mid-70s. They looked at quadratic supply rates, but nonlinear dynamics. But you could ask more questions. What about nonlinear systems, non-quadratic supplies and constraints? What about the relation between dissipativity and the minimum principle? What about the relation of dissipativity to dynamic programming? And maybe a slightly provocative question. What about the question whether Willems was the first to use dissipation inequalities in optimal control? And these are my questions for this first part of this talk, before I'll show you how this all relates to the turnpike property. So we take a simple optimal control problem. I will not worry about the regularity conditions to ensure existence and uniqueness of controls and stuff like that. But it's finite dimensional, and I'm only considering input constraints. If you want to solve that, you could think about the minimum principle. Then classically, you define the optimal control Hamiltonian. You end up with a two-point boundary value problem, which has the defining condition that you have to minimize the Hamiltonian along optimal trajectories, somewhere stated here. You may wonder if you have heard about the minimum principle as a maximum principle. Why is that the case? Simply a sign convention on this multiplier. These are necessary conditions, lead to open loop optimal controls. The counterpart is Bellman dynamic programming, which in continuous time leads to the Hamilton-Jacobi-Bellman equation, assuming differentiability. This takes this form. It's the first order partial differential equation in this object here in the optimal value function. What is nice about this, if you can find the value function, if you have it, just look at the left-hand side. If you give me x and the value function, I can solve the minimization at one point in time for you, gives me an optimal feedback. So dynamic programming always gives us optimal feedbacks. But where's dissipativity? Well, let's do the following experiment. We take the dissipation inequality, we plug in an optimal trajectory pair, however I have computed it, we integrate our dissipation inequality, and we end up with this integral dissipation inequality, which has here on the right-hand side precisely the defining equation for the optimal value function. So in other words, dissipation inequalities directly give you sub-solutions to the Hamilton-Jacobi-Bellman equation, or in more simple words, lower bounds on the optimal value function. Now, was Willems the first to use that? I'll try to explain this to you using a very simple optimal control problem, or rather simple. This one here with the dynamics being x dot equals u. So the simplest linear dynamics you can think of can be vector valued, can be scalar, that doesn't matter. Optimal control problems of this form are actually rewriting calculus of variations problems. The calculus of variations you can trace down to Leibniz, Euler, Lagrange, Bernoulli. It's about 300 years old by now. Now, calculus of variations was heavily investigated late 1900s, early 1900s. And one person who did work a lot on this was a Greek fellow, Konstantin Karatheodori. His major work was a treatise, a book, a two-part book on calculus of variations in 1935. And in there he gives a sufficient condition for the existence of optimal solutions to this problem. How do these sufficient conditions look like? If there exists k of t and x, we would call this a feedback, and a function s of t and x, such that for all points in time, this partial differential equation holds, and for all suboptimal controls u, which are close to the feedback candidate, and feasible, so they satisfy the terminal conditions, this inequality holds. Now, if we look at these two equations sharply, then, how does this look like? What if I would combine them? If I would combine them, this looks very much, I have to minimize here. I have to look for the smallest value on the right-hand side. Then I end up with this equation. That's what we have already seen. This reminds a hell of a lot of the HGBE, or of the minimization requirement in the minimum principle if I look at the right-hand side. But if I only take the second equation, and bring this term to the other side, well, this is clearly a dissipation inequality. So already prior to Willems, about 30, 40 years, in the calculus of variations, Kara-Theodori came about with these sufficient conditions which rely intrinsically on a dissipation concept. That was a great surprise to me when I first saw these equations. And to tell you how this is valued, if you talk to people who work still on calculus of variations, this concept of Kara-Theodori is known as the royal road to the calculus of variations, as the most elegant approach to a solution. So I will not tarnish any of Willems' reputation. I think that might be a prime example, similar to the minimum principle, that important concepts have been rediscovered in the development several times, and it's quite clear that the dissipation inequalities are key here. That was my prelude, but by training, Elena has mentioned, I'm a control engineer. At the end of the day, I want to apply, I want to implement optimal controls. How could I do that? Based on what I've said. I could take dynamic programming, I would get an optimal feedback, but still optimal value functions are difficult to compute. Some of you might say, hey, hang on, there's reinforcement learning. Can't we do a hell of a lot with it? Yes, but only if you can probe your system very often, if you can generate a lot of data. If you can't do that, then in a lot of situations that is still difficult to do. You could go the minimum principle route. The catch is you get an open loop optimal feedback, which depends on the initial condition which you have encoded in the optimal control problem, so you don't get feedback. It's open loop optimal controls. The idea to then simply say, if this is easier to compute than this, why not do this often? You can trace this back to the 60s. Reappeared several times, at least 4 or 5 times in the 60s already in the literature. So what you do here is you solve one OCP, get an open loop optimal input, apply it to a system, then you measure the next state and solve it again. Now, why is that of interest? This is of interest because now I don't solve one optimal control problem, I talk about a sequence of optimal control problems. I talk about a sequence of optimal control problems parametrized in the initial condition of the dynamics. So, in other words, I talk about a parametric optimal control problem. And now you can think about, if you know optimal control, what do we know about parametric optimal control problems? That's far from a standard topic. And what I want to explore with you now is how we can use dissipativity and dissipation inequalities to understand the solution structure of parametric optimal control problems. And this brings me to turnpike properties and then a bit further down the road to MPC. I give you a nutshell, a very simple example. Scalar dynamics, that's like a controlled logistic equation. X is the fish density in a habitat. The objective consists of 3 terms. The cost of feeding the fish, so we're not talking about the open sea, we're talking about like an aqua farm where we have to feed the fish. The cost of fishing, and this term here models the revenue I make, because fish density times fishing rate times the price integrated over gives me an amount of money that I want to earn. I will look at this problem for a set of initial conditions and for different horizons under some constraints. If we solve that, you can do this analytically or numerically, and this is the solution you get. You get a solution if you start at a low fish density, which tells you don't fish at all, let the fish population grow, fish at a constant rate, fish as much as you can. Now we vary the initial condition, we vary the horizon length, and all these solutions remain structurally similar. They all approach this steady state in the middle. And why is that? Well, this becomes clear if we look a bit more into the geometry of the problem. And there it comes to play that we have a scalar state variable and a scalar input, because I can plot you the optimization landscape on which the optimal control problem acts. These are the contour lines of this integrand here. Up here, I would earn the most money. But of course, underlying, there's the flow of the differential equation, there are the dynamics. I cannot be everywhere in this space and cannot enforce any arbitrary paths in this space. The black line, that's the set of steady states for my system. So what the optimal solutions do is, if I start with small values of x, I keep u at 0, x grows until a certain rate, then u jumps to a certain steady state value, trajectories stay here, and then I jump again fish as much as I can, and I move down here. If I start at high values of x, it's the other way around. I fish as much as I can, jump down here, stay here, but then I jump back up. If you look sharply at this point, that's the best equilibrium I can find. So automatically, the optimal solution finds the best equilibrium. And if you observe something like this, that for different initial conditions and different horizons, all the solutions are structurally similar, you observe what is called the turnpike property. But all of you attended the nice banquet yesterday evening. Some of you might be as tired, even more tired than I am this morning. Who has heard the term turnpike before? Or who has it in his active vocabulary? Some of you do, okay, that's nice, but not all of you, despite all of you using English as your language for your job, in academia. What is a turnpike? A turnpike is a turning pike. It used to be the point where you would pay the fee to use a road or to cross a bridge. That's a turnpike. That is the turnpike right behind this conference building at the parking lot. The east coast of the US, the word turnpike is used to refer to this situation, when you pay your usage fee to use a highway. There is a Massachusetts turnpike, there's a New Jersey turnpike. And how did this name come about for this phenomenon? That dates back to 1954 to a book of Samuelson, Solow, and Dorfman. The first two, Samuelson and Solow, did win the Nobel Prize in economics independently of each other for independent contributions. And they looked at what I would call discrete time optimal control with linear dynamics and linear constraints and linear objectives. So linear programming with multi-stage constraints. They observed a turnpike and they explained it like a turnpike/highway paralleled by a network of minor roads, and it always pays to get onto the turnpike, cover distance at the best rate of travel before you take the exit and arrive at your destination. Now, if we want to give that a bit more formal definition, and I spare a lot of mathematical details, the iconic picture is that the trajectories approach a steady state, a dedicated steady state x bar, to which I will refer simply as the turnpike, stay there epsilon close and may or may not depart at the end. And if we want to formalize it, we want to characterize the time we spend in this epsilon neighborhood. So a formal definition of a turnpike can look like, let's bound the time optimal pairs x star u star spent in an epsilon ball around x bar u bar by something which is not only finite but independent of the horizon length. So if Bellman gives me an initial condition and I have this bound, and I can choose a horizon to make sure that my solutions will be epsilon close. Now, is this a freak phenomenon or does it appear often? Sorry for the crowded slide, but let me give you a walkthrough. This here is a paper by Anderson and Kokotovich from '87. They depict this on the very first page. I would call this a turnpike. They don't use the term. They called it a dichotomy in optimal control, referring to slow timescales and fast timescales. A paper by Jean-Michel Coron on protein folding. They have the turnpike, not in the title, but in their plots. Shape design for mechanical structures, that it was Enrique has been working on a lot of time. Continuous manufacturing, production planning. So in all branches of engineering and science where you can use optimal control, this problem pops up. So it doesn't pop up in all optimal control problems, but it pops up in a lot of them. And that's why we're interested in it and want to understand it. In order to take a dissipativity approach to it, I have to do two changes. I have to change my dissipation inequality, and I have to change where I require dissipation. And this was the dissipation inequality we used so far. I will change it in a minute. And this was where I require dissipation for all possible trajectories. And that can be quite restrictive. But I look at optimal control. I'm brave enough to assume optimal controls exist. So my first changes, I require dissipativity only on the set of trajectories which are optimal. Let me call this the optimal behavior. You have to be super careful here if this is really a behavior in the Willems sense, because if I truncate it in time, the elements of it still satisfy the dynamics, but not necessarily an optimality condition. There's some details one has to watch out for. So this is where I want to have dissipativity, but what kind of dissipativity? I change my supply rate by adding here the stage cost evaluated at a steady state pair, which will become the turnpike. And that's why I call this dissipativity notion, or one calls this dissipativity with respect to a steady state pair. I also want to make this dissipation inequality strict. I add here a class K function, and it's no coincidence that I color this in red like the decay term in the Lyapunov function, because in our analysis it plays the very same role. And in the class K function, I evaluate the difference of the optimal pair at a given point time t to the turnpike pair. And since I only talk about optimal trajectories, I do not say the system is dissipative, I say the optimal control problem, or in short, the OCP is dissipative. And if you don't know what the class K function is, take it as the identity. It's a monotonously increasing function of a scalar argument 0 at 0. So how can we proceed with that? This is my optimal control problem of a set of initial conditions, inequality constraints. That's my stage cost. If we have the structure of this strict dissipation inequality, abbreviated as SDI, one can show that X bar U bar is not only a steady, does not only need to be a steady state, it is by the structure of strict dissipation the unique globally optimal solution of this problem. And what is this problem? Well, it has the same objective, but without the integral. It has the same dynamics, but at steady state, and has the same constraints. It's the steady state counterpart of the optimal control problem. Why is it globally optimal? Strict dissipation at steady state makes the change in storage vanish. You bring the class K function to the other side, and this structure certifies global optimality and uniqueness of X bar U bar. Now we massage the problem. I don't show you the details. We find that if we have the strict dissipation on the behavior of optimal trajectories plus a reachability condition for this turnpike pair, we have the turnpike at this pair. And the bound takes a very specific structure. There is an upper bound on the performance and on the storage in the denominator, and the class K function evaluated for the neighborhood on which I look at appears down here, which means epsilon equals 0 is a special case. We can handle them. I spare you the detail. What this means graphically is that this amount of time, this stretch of time here, is bounded from above by this bound. That's what I get. It doesn't matter here whether here's an extra excursion of the neighborhood or not. And when we were there, we were thinking, can we go back? Can we have, similar to Lyapunov theory, a converse result, which assumes the turnpike property and then tries to get back to strict dissipativity? And in what we did, we needed second-order sufficient conditions on this stationary optimization problem. So a kind of geometry on the KKT conditions on this simple optimization problem in Rn, plus a few technical details. There exists a second route, how you can get from turnpike to strict dissipativity. That was done by Matthias Müller and Lars Grüner. Matthias is up there on the floor. They used not only discrete time, but also a different concept of turnpikes and slightly suboptimal solutions to have a converse result. So it's safe to say that strict dissipativity and turnpike properties are two sides of the same coin, and the coin is here the behavior of the optimal trajectories, the behavior formed by the optimal trajectories. If you know about optimization, you know about dual variables. I have not mentioned a single dual variable so far. How can that be? Well, what I've been looking at is this route, the optimal control problem, its stationary counterpart. Now, we look at the optimality conditions, which is the minimum principle, and we look at the minimum principle now at steady state. So we do the same process. We have our dynamics, we look at it at steady state, and then it turns out if I now look at the optimality conditions of this problem, I end up at the same set of conditions. So it commutes optimize, steady state, or steady state, optimize. You always end up at the KKT conditions of this problem if you do it correctly. What does this mean? Turnpikes correspond in their primal dual nature, in decision variables and multipliers, to steady states of these dynamics. So if I want to have an infinite horizon analysis in the nonlinear setting, I have to understand the asymptotics of these dynamics. And that's what we set off to do. We looked at an infinite horizon optimal control problem of this form, said, okay, we don't know if the minimum is finite. If it exists, let's write infimum here. You show dissipativity gives you that the infinite horizon optimal value function is finite, which is very nice to have. Then we had one circle of results, not circular results, but a circle of results, showing primal attractivity that on the infinite horizon you converge to the turnpike steady state. You get local exponential stability by constructing a Lyapunov function, which includes the infinite horizon optimal value function and the storage function. So both things come together there. We can mirror that for the dual variables. And what I think is most interesting is this geometric relation, which you can simply obtain by differentiating this Lyapunov function at the turnpike steady state, which tells you the gradients at the turnpike of any infinite horizon optimal value function, modulo, assuming differentiability, matches minus the gradient of any storage function evaluated at the same point, and they match this Lagrange multiplier, which I can obtain by solving a single steady state optimization problem in Rn. So I have a lot of geometric information here. What can you do with this? I will spare you a lot of technical details, but what happened in the MPC community is a lot of results in dissipativity MPC, first with what we call terminal ingredients and penalties and end constraints you get back under dissipativity. Asymptotic stability of the turnpike, which is the globally optimal steady state. Then Lars Grüner came along and said, let's drop the terminal constraints and the terminal penalty, and what they found is practical asymptotic stability, and of course there were a few other people also involved. We did a bit on recursive feasibility, there are also other works, but what is the gist here? What does all this work do? It tries to have more general MPC formulations, more general than X transposed QX, U transposed RU, with Q and R positive definite. So you want to be able to apply MPC with a larger set of cost functions. Is that interesting? Well, it depends what kind of practical asymptotic stability we have here. So let me show you how this looks. A simple bilinear example taken from chemical engineering. Here is our cost function. It is polynomial, but not really of standard form. There is no X transposed XU form term. Red are predicted trajectories. Black are closed loop trajectories here for 3 initial conditions. I initialize at the turnpike steady state and a bit beyond, and I see all the solutions converge somewhere, but not quite at the turnpike. That becomes very visible if I go to the steady state, to the state space. This is the turnpike. My solutions go from here to here, from here to here, from here to here. So there's an offset. And that's annoying in some sense. I do MPC, I optimize on the finite horizon. I know there's a unique globally optimal steady state, but my MPC scheme doesn't converge to. It turns out that the offset that I find here decays with the horizon. Now you can do 2 things. You can understand why this is the case and prove the structure of this decay of the offset, or you can ask, how can I get rid of it? But I want to get rid of it without imposing terminal constraints, because they create a lot of issues if I want to deploy my control on small hardware or anywhere else. And the simple solution Mario Zanon and myself came up with is adding a linear end penalty here, which takes the steady state Lagrange multiplier. And what we do by this, from a geometric point of view, we make sure that our finite horizon optimal value function from the MPC evaluated at the optimal steady state matches the geometry of the infinite horizon one. It's a very simple trick, then a lot of technical work, and you can show asymptotic stability. What does this mean? Well, instead of having this offset, we converge there. And the good news is, I do not even need to compute this. I can learn this value from my previous predictions. I can estimate it for unknown cost functions. So you can combine this very nicely with ideas of learning and adaptation to uncertain environments. And the real neat feature is, if now your stage cost changes a bit because there are prices in there and changes once in a while, your MPC scheme will again track the best optimal steady state. And you don't have to do anything. It automatically follows the best optimal steady state. That is kind of nice. So let me sum up this part of the lecture, plenary. I've explored the relation between strict dissipativity and optimal control. I've shown you the links between strict dissipativity and turnpike properties. And what I like about the turnpike property, and I think one cannot say this often enough, it is a property of parametric optimal control problems. Parametric in the initial condition and the horizon length. And this parametrization in the initial condition helps us to use it for MPC, because MPC is parametric optimal control, nothing else. It's solving a sequence of optimal control problems. There exist manifold extensions, stochastic, time-varying, periodic, and so on and so forth. But what is again the gist? This is classic MPC with stage costs like this, and also nonlinear dynamics, linear dynamics, PDEs. The dissipativity-based approach generalizes this because if I have a cost function like this with Q and R positive definite, I can always choose a constant storage to say it's a dissipativity-based approach. So it's a true generalization. However, how do I check dissipativity? Verifying such a dissipation inequality is as complex as computing solutions or as computing the Lyapunov equation. That's not an easy problem. So I think the most promising tool in our arsenal, or toolbox, if we are in a nonlinear setting, would be sum of squares programming. Has made huge progress, but it's not something you apply to large-scale industrial systems. It simply doesn't scale that well. I'm an engineer by training. Maybe I should just run a numerical simulation study. But most of us would say there's not enough rigor in that to use that as a verification of the dissipativity. So it seems like a dead end. If, however, we change the perspective and ask the question, is strict dissipativity an assumption we have to verify, or is it a design guideline? The picture changes. What do I mean to say? If I design an MPC scheme designed to stabilize, here's something at X bar, what do? Take a pen and paper, write down an optimal control problem, then I start choosing the terms. The stage cost, the end penalty, the horizon length, terminal ingredients, maybe the other constraints, maybe I design them as well. We design optimal control problems when we do feedback control. So what we do by this is clearly we shape the behavior of predicted optimal trajectories by our choices. And what is the one requirement that we want to have if we do stabilization? Well, in the best case, in the ideal case, we have an infinite horizon in the MPC. That would give us the best possible performance. We wouldn't have any disturbances and a perfect model. So let's take that ideal case. In that ideal case, I want to design this OCP such that any predicted infinite horizon trajectory goes to my target steady state. That is how I should design my OCP. If your OCP, your optimal control problem, doesn't satisfy this, why would I use it in closed loop, right? What have I shown you in dissipativity? It gives us precisely this property if we have strict dissipativity on this behavior. So my conjecture, if not claim, is that stabilizing MPC schemes induce dissipativity on the behavior of their predicted trajectories through the design of the optimal control problem. So dissipativity is not an assumption we make. It's under the hood, it's an implicit design requirement. And we will struggle very hard to avoid satisfying it if we aim at stabilization. That's quite impossible, I would say. And with this, I want to stop discussing MPC and want to come to two extensions. If you have listened to Stefano's semi-plenary on Wednesday, he has talked about port Hamiltonian systems. I will briefly touch upon this and then talk about stochastic systems. This here is a very simple system. It's linear, finite dimensional. It has a very particular structure, a skew-symmetric matrix J, positive semi-definite matrix R. It's a port Hamiltonian system. This is the dissipation. That's the interconnection. This matrix Q here relates to the underlying energy Hamiltonian, which is a quadratic form. So in other words, this system is passive with this supply rate. This structure and more general passive structures have been exploited for nonlinear and linear feedback control because you can have similar structures to nonlinear world as well, under this slogan by Romeo Ortega and co-authors, putting energy back in control. So let me ask, can I put energy back in optimal control? How would this look like? I take this simple example. I use this optimal control problem. Objective is the supply rate. I have initial conditions, terminal conditions, and observe that in this optimal control problem now I want to minimize the supplied physical energy to the system. That is something very different than minimizing over U square, which is great for numerical optimization, but doesn't have the physical unit of power. U square is not power. U transposed Y, that's power. In our previous analysis, dissipation entered through this term, and then the optimal trajectories tried to make this term small, so X star had to go to X bar. For port Hamiltonian system, dissipation enters through the kernel of the dissipation matrix. So this is a linear subspace. So what will happen in the optimal trajectories, without all the details, the optimal trajectories will go to a subspace where you don't dissipate energy. So suddenly, two things happen. The turnpike objects become more general. They go from steady state to linear subspaces. In the nonlinear world, they become manifolds. And these objects have a physical interpretation. They relate to the part of the state space where you do not dissipate energy. So in the linear setting, the subspace is the energy conserving subspace. In the nonlinear setting for thermodynamic systems, it becomes the manifold of thermodynamic equilibria. You can use that. Manuel Schaller, Karl Wortmann, and other colleagues from Stuttgart used this idea, I was not involved there, to look at vibration damping in high-rise structures, and they could show a controller which uses this objective would consume less energy if you deploy it, and really physical energy. So there's more to explore there, but this concept goes through all kinds of variations of port Hamiltonian systems, PDEs, DAEs, and so on and so forth. You could also ask, what about discrete time systems? Here's a toy example, a scalar discrete time system. We solve it, we see the turnpike. That's not my point. That's way too simple for you. And it's way too simple for what we need in applications. What is the applications I think of? I think about stochastic systems that appear in energy systems. In energy systems, renewables are stochastic. Your demand, your energy consumption is stochastic. Market clearing is stochastic. It's very hard to predict what the market outcome will be. The catch is all the stochastic uncertainty is non-Gaussian, unless you look at a large-scale system where a lot of the uncertainty sources add up. But that is not what is happening. So we want to understand what happens in an optimal control problem if there's stochastic non-Gaussian uncertainty entering here through this boldface variable V. Boldface variables are for me random variables here, or capital letters. I solve this problem, I look at realization paths of the optimal control system, that's what I see. So where is the turnpike in stochastic optimal control problems? It's a fair question. The first thing we have to do is we have to understand what is the counterpart to the stationary optimization problem. And the counterpart becomes a stationary stochastic process. This looks like this, and you may wonder, oops, is this yet another font glitch that here's no summation appearing because you have dynamics here? No, a stationary stochastic process is a dynamic system in random variables. What is stationary is the underlying distributions of x, u, and w. So the statistics are at steady state, not necessarily the random variables as such. And the other thing you might wonder, why do I write the control action as a random variable, not as a policy that's más o menos the same? It is a bit more general with random variables and illustrates more the structure what is there. So we look again at our realization paths, look at the distributions. Oh yes, this looks the same. So the turnpike is not lost, but that's not all. Take another example, expected value here of this part of the course, some variance penalization, linear dynamics, Gaussian initial condition, uniformly distributed noise. We solve the problem, look at the PDFs, how they evolve over time. That's the Gaussian initial condition of one of the state variables. And you see this boxy-shaped probability density function. This box shapes relates to this uniform distribution. So we see a turnpike in distribution. Can we see more? Well, let's do an experiment that was suggested by Lars when we did this work, by Lars Grüner. We compute the optimal solution in random variables, which is a policy. Then I fix the disturbance. I fix the scenario I look at in terms of renewable feed-in and demand. And I sample initial conditions. And now for each initial condition, I simulate the system for the same realization of the disturbance with the policies. But the initial conditions differ. But all these solutions, they are spread out here. They converge to the same time-varying trajectory that there's a turnpike underlying you see here at these leaving arcs. So in the realization paths, we see, again, a turnpike. But the realizations have to be the same for the turnpike to emerge, which makes a lot of sense. This means if the realizations are the same, the system behaves the same. That makes a lot of sense, but this is what we wanted to understand. So we see turnpikes in moments, distributions, random variables, and this pathwise one. And this is where we head off in a joint project. We looked at an optimal control problem in random variables. I will spare you all the details. I just want to point you to some structure of the dissipation inequality we use. It's time varying because the stationary stochastic process is time varying. This depends on the statistical information of the disturbance sequence. And here, the class K function we use is in a distance on random variables. And if we do that, we get a turnpike in random variables and a pathwise turnpike. You could say, I don't want to compute on random variables. That's too complicated. Then you go to the Markov decision process. You have a decision operator. Then your state variables are probability measures, incredibly complicated objects. What is nice, the probability measure as such is a deterministic object. Right? It just describes stochasticity. I can write down another dissipation inequality with a strictness term. And in this strictness term, this is where you can plug in Wasserstein metrics or other metrics, and you get all these nice properties again, also on the space of probability measures. And now look where our common control thinking is. The common control thinking is here in the moment turnpike. So when you look at stochasticity in moments, you have lost a lot of information. You cannot explain this pathwise turnpike property that I've shown you. You need to go to the space of random variables and work there. And all the credit for the fantastic work here should go to Jonas Schiesel, because that's part of his PhD thesis with Lars, and we did this in a joint, or we do this in a joint project. Okay, let me come to the last part of this talk. I want to talk in another aspect of our very recent work, and this is dissipativity-based design for deep learning. All of you have seen neural networks before. I look at a very simple problem, classification. I have on the input side of the networks points, sample points, they're colored. I want to propagate them through the network, such in the output space I can decide what is a green point, what is a blue point. I want to classify. I have data pairs, where Y is the label which says the color, and that's the data point. That's the data point. I want to learn a map. What is the network architecture I use? I use residual networks, which in discrete time look like this. Then you see already if this is the network state and it is of constant dimensions, like a constant width neural network, but the depth could vary. It's like a time horizon, the depth. Why is this interesting? Because this is a discretization of a neural ODE. Of course, I can also could use tools for analysis from neural ODEs like Bellman and Polo Tawada did recently. So I look first at the data propagation problem. I have m data points propagated over a network of n layers. For each data point marked by the subscript I have my neural network dynamics. What steers the data through the network is the weights and biases. How do we find those? We optimize over something which machine learning people call loss function. I evaluate the loss function for each data pair and average. If you look at that problem sharply, this is an optimal control problem. These are my ensemble dynamics, and here the 1 over m and the sum does not let it fool you. That's an end penalty, because I evaluate what does the network do at the end of it, in the output layer. I abstract this problem, and now what I want to do is, I want to think about dissipativity-informed formulations. And here, what I have added in red didn't appear here. That's a regularization term. My machine learning colleagues call this the weight decay, because it enforces decay of weights. And that's the stage cost they always use in different variations. I want to now think about, can we design this stage cost? And I'll put on my turnpike goggles. I assume my training problem for the neural networks has the turnpike. Then I have the following situation. This is an optimal trajectory. If this is an epsilon tube, I have the red bound for the blue time, that I'm outside of an epsilon neighborhood. Now I split my time horizon. I also look at the green part where I'm in the epsilon neighborhood. Then I fix epsilon and pick a horizon such that horizon length minus my bound evaluated for epsilon is larger, or my horizon has to be somewhere here. The yellow bit of time, part of time that I get is this part in time. But this is indeed a lower bound for the time I spent in the epsilon neighborhood. So if I have the turnpike property in my training problem, I can tell you at the end of it, you will be close to what we call the turnpike, to the best steady state. So what is my line of thinking here? Let us design a training problem such that I can give you this bound, thereby give you a bound on the depth that you need to get close to a point I can choose. So I want to design the training problem. And if once we do this, sorry, with apologies to Willems, the rest is mathematics. We get a depth bound which certifies with simple Lipschitz assumptions performance in terms of loss, in terms of suboptimality. And if there are problems where getting epsilon close is good enough, I can certify what machine learning people call empirical risk. How does this unfold? Red is the given loss function of machine learning colleagues. This is what I designed. A simple way to do this is I take their stage cost, look for a stationary minimizer of that, which is a simple problem for ResNet. We call them ResNets because the entire state space is covered by steady states. I take one of the minimizers, plug it in here, an LQ-like tracking cost, and this goes back in here. If we do that on this Swiss data roll example, toy example, the trajectories, the training trajectories, network depth, network state change from this to this. They go where they should be very rapidly. On this data, I can a posteriori evaluate the bounds and find that they're very tight. 5, 6 layers do the job. My bound says something between 7 and 8 with a lot of noisy data, even a bit less. So the bounds seem to be not too bad. Now we change the problem, make it much more complicated. MNIST, that's recognition distinguishing handwritten letters. If a machine learning person is tasked, give me a shallow network that solves that problem, what do? They solve their standard training formulation, that's this one, we have already seen this, with their favorite loss function for 60 layers, 40, and so on. And eventually they find out 10 layers will do the job. But it's an empirical process. They have to run a lot of numerical simulations, and a lot of physical energy is dumped into this as we speak. What we did, we say, let's take another look at your loss function. Here we looked at the soft cross entropy, and we could show, if we look at, again, the steady state minimization problem, we find the set of minimizers is a linear subspace. We say, oh, if that's a linear subspace and I have sufficient curvature, I can pull this thing into here, and I get back a strictly dissipative training formulation. And what happens is that this is the training problem we then suggested, which completely changes neural network architecture because you evaluate loss at hidden layers, which is, let's say, you have a lot of discussions with machine learning colleagues if you propose something like this, but this is how the loss behaves over network layers. So I solve it once for a deep network, I plot my loss evolution over the layers, and can tell you 10 layers will do the job. And I don't have to recompute. I could either prune the network and head off with what I have here, or I could say, hey, I know 10 layers is good, let's re-optimize with the pruned solution as an initial guess. And then, of course, the optimization goes faster. So with the rightly chosen training formulation, I can give insights into what is good hyperparameters of the architecture here, the depth. Of course, reality is not as simple. What about validation? I don't show you the plots here. There's, between our formulation and the standard ones, that's roughly the same. There we don't see a lot of loss of validation performance. Generalization properties, that's something we currently work on. Can we give guarantees that we perform well on data we haven't seen in the training? What about going to other architectures? Well, this dissipativity-informed training formulation, yes, the proofs become simple for ResNets, but the ideas don't depend on the ResNet architecture. They depend on very, very different structures. And with this, it's about time to sum up. I've tried, well, time should be good, I think. To sum up, what have I tried to tell you? I've tried to show you a string of results and dissipativity-based analysis of optimal control problems. I've chosen here the continuous time route, most of the results to go through directly in discrete time. And you can make this go to really complex situations. And then we have mirrored this into dissipativity-informed design. And I've shown you this for the neural network training where we design an optimal control problem, because this is what we do as controls people. We formulate problems that we want to solve. And we have done it for the MPC. But of course, dissipativity-informed design goes far beyond that. If you think about the work on using dissipativity to designing optimization algorithms, for instance, that's another form of dissipativity-informed design. And I think we haven't seen the end of it at this point. There's much more we can do. So there only remains two things to do. I have to say huge thanks to all the wonderful collaborators and brilliant PhD students I had the pleasure to work with throughout all the years, some of which are in the audience. And I'm incredibly thankful and indebted to this wonderful collaboration throughout the years. And I have to say, Evcharisto to all of you for coming here to this first morning plenary on the last day of the conference. Thank you.
thank you very much, Tim, for this amazing, insightful talk, really so rich. I think it's going to take me 2 weeks to understand the full content of it because we're so far-reaching. I'm really impressed. And were it not that the talk is part of an award, you would deserve an award for the talk itself. So thank you so much. And so, as I mentioned, this is a part of the award. So it's my pleasure to give you this plaque as a recognition for the European Control Award. If I can make a last comment, I was particularly, happy because you mentioned several times Jan Willems. He was one of my mentors. I worked with him not on dissipativity, but on behavior in the late 90s, and he's, to me, one of the amazing, giants of the research in our community. So thank you very much, and enjoy the rest of the conference.